Hello. Yeah, so students put please like mute all your video and audio so that we can be more stable, right, when recording. Yep. Okay, there are 20 people joined already. I need to new share desktop. Okay, so I will just start. So yeah, so I feel very nervous. So I will just stop the video and share the notes. If you want to ask a question, just ask. You can unmute yourself, and or you can type in the chat window. I don't know how to do that. Stop share and screen share. Okay, so we start. Let's start. Okay. So I want to make sure I'm recording now, right? Yeah. Okay. So let's start. So okay. So I cannot see all of you. So I'll just keep talking. So if you have questions, you can raise your hand, right? So there's some button. You can raise your hand, and you can also clap the hand. Right? Also, you can use the chat button. So. So hopefully you can get people, for students who cannot get into the meeting today, the first online meeting. So we probably can get the video. So in 5 days, because it's very long. So it takes some time, and many people using Zoom now. So let's start. So we haven't finished backward martingales last like maybe 20 days ago. So it's a long time ago, and things changed. So changed a lot after last lectures. But let me. So yeah, it feels because I cannot see you, right? So things goes. But let me know, right, if you have questions. Okay, so last time we talked about the proof using backward martingales of the classical Hewitt-Savage 0-1 theory. So which is here. So this is a Hewitt-Savage 0-1 theory. So it is assumed, right? If you have a sequence of IID random variables, and this E is the exchangeable sigma field. So we claim this exchangeable sigma field is a trivial sigma field for any set, right? It's either empty or the whole set, right? Okay, so we already proved this. We already proved this Hewitt-Savage 0-1 law, and you can find proof in the textbook or in this notes below. As I said, right, the proof. So actually, the proof is more important because it's useful if you So I think it's useful because I'm doing related to this, right? Like if you consider high dimensional statistics or large n particles, right? Many particle system. So the techniques used here is very useful. Okay. So this is a proof we can find that. And in particular, right, so there's this one part, right, there's a small conclusion here. So I covered in last lecture. Right? So what does this says, right? This says if you consider a conditional expectation, so it's a conditional expectation of random variable x projected to a sigma field G. So if this random variable, right, is independent of x itself, right? So then this conditional expectation is just itself, not just itself, it's just the Euler expectation, right? So you can prove here, right, is the third problem in the midterm. Okay. Okay, so this is the Huviert 0-1 law. So I think we just stop here, right? We stop here on the definite theory. So definite theory actually is very important. It's kind of related to the foundation of statistics, right? Like or probability. Usually when we say like probability, right? What is a probability, right? So there's a few different point of view, right? So this is a very old work, right? It's like at least maybe almost 100 years old. So it's called definite theory. Right? What does this say? It says if we have a sequence of random variables, not just IID, right? Not IID, not necessarily IID. But so if we have a sequence of exchangeable variables and we conditional on the like exchangeable sigma field. So this is E, right? It's exchangeable sigma field. So then the random variables, so actually IID, right? If we're conditional on the property like exchangeable sigma field is IID. This might looks not a very clear, right? So why, but the idea, right? So if we put in the intuitive way, what a definite theory says, right? So it actually says the following. I'll just show you the next one. This theory. So this is the easiest theory of definite theory, right? So what does this say, right? This actually says, right, conditional on the exchangeable sigma field E. So all x, so x1 to xn, right? The sequence is IID. So which means original sequence actually is an integral or a mixture of IID sequence. So this is one example. You can find a very elementary proof. Actually, I find a very elementary proof of this theory, right? This is the classical version of definite theory. So like last year, I guess I find that last year. So if x1, x2 is exchangeable and only takes values between 0, 1, right? Either 0 or 1, right? Like you flip a coin, a fair coin, not necessarily fair coin. You flips a coin, so it can be either positive, 0 or 1, right? So if this sequence is exchangeable, right, then we can find a probability distribution on 0, 1 such that so this event, right, can be represented, right, can be represented as so theta k 1 minus theta n minus k. This means the probability like head up is theta, right? So then this is actually IID, right? So you just do the product rule. And here we only have exchangeability, right? Not necessarily IID, right? So it's in the end, it's not just this part, but the integral of this part. So F actually is a density function from 0 to 1. All right, so it gives this for the probability theta. So yeah, you can find the proof, very elementary proof of this. That I can also put the paper I found in the Dropbox. You can try to read that. Actually, it's a very short proof. So I need to check. I need to check if you have any questions, but I don't know how to check. So any questions? Yeah, if you want to ask questions, you can unmute yourself. Questions? Yeah, but I cannot hear you. So there's one.
Can you hear me?
Yeah. Go ahead.
Okay. Oh, sorry. So is it like this F is a prior? I think so, right?
F, you mean the capital F, right?
Yeah. To look. Yeah.
Yeah, I think so, right? You say it's a prior.
We are integrating over this prior. I think like.
Yeah, probably, but I don't see the connection, right? So yeah, so I don't see. Yeah, it's really related to a priori, right? Posteriori distribution, but I'm not sure this F is a priori, right?
Okay.
So this F might be the real one, right? Let's say if we don't know the probability, like heads up in flipping a coin, so F this is actually the real knowledge. I don't know, right? Let's say we only know they're exchangeable, right? So we can, yeah. So F is actually all the knowledge we have, right? So
okay.
the target, the kind of the target we want to find, yeah.
Could you show the previous theorem again? The one right above this one?
You mean this year?
Okay. No, yeah.
This year, right?
Okay. Yeah. No, I confused myself. Okay, I got it.
This theory actually is exactly the same. So this is a general form of the definite theory.
Okay.
Yeah. So this is a general form. And what's the theory I'm showing now is a specific form, right? It's a specific form.
Okay.
So if you like, if you don't consider this part, so actually they are IID, right? They are IID.
All right.
Yeah.
Yeah. Well,
so it's just, yeah. Yeah, if conditional on like the exchangeable sigma field, you get IID. Yeah, this is exactly the same theory. So originally, the definite theory is very earlier. I think in last century, like 20s or 30s. Savage maybe a little bit later, right? So it's 1956. Yeah. So actually, there are a lot of books discussing like functional statistics. I don't know a lot of that, but if you just search theory or definitive type theory, I think there are huge literature on that. Yeah. So why I know this, right? So why I know this, right? Because so my major work, right, is on like doing n-particle system. So in n-particle system, we don't have like a sequence of random variables, right? So we have like n random variables. So those n random variables, so actually are exchangeable. So usually so in statistical physics setting, usually we consider those n particles might be molecule, like in plasma ions, right? So they are usually we assume indistinguishable. They are indistinguishable, right? They are exchangeable. So we have fixed number of particles, a fixed number, we call the number of particles n. So they have the exchangeability condition. It's not exactly the same as the definite theory or the Cuvier-Savage theory. So I'm not sure it's called Cuvier-Savage. So there's another version of definite theory, right? So for instance, here, if we have a sequence, right? So in the end, we really can write this is kind of distribution of n particle, and this we can exactly write as the mixture of IID. But so this is because we have a sequence, right? So this n goes to infinity. But if we just do a truncation, right, the fixed number n, so this is not really true, but this is almost true, right? You can take the difference of the first one with the second one. So you can do some estimate, right? So this is kind of, yeah, I don't know the name for that. It's kind of some larger limit as well. Okay, so any other questions? Okay, so if we move to the next section, also, I think if we just do audio, right? So I mean, even you discuss with each other, it shouldn't be a huge problem. Right? I'm not sure. So yeah. So if you have a question, let me know. I can even show like in the Blackboard. So I connect. I can show you. Right? I can show you. Let's say stop share. I can share the iPad. Can you see that? Okay. So for instance, right? So we can write something here, right? So for instance, right, you can. So if you connect iPad by using like lightning to some USB cable, you can just project the screen on your iPad you can see that, right? You can see that. So I don't know how to spell definite. So like definite. Definity, right? So you can do a lot of things here. So basically, sometimes, right? So if you are traveling, right, even not at this very bad season, right? So you want to travel, right? So you can give a Zoom lecture, right? so it's actually very good too. So anyway, if you want to ask questions, I can show you, right? But otherwise, let's go. So we need to talk a little bit about the last part. Also, it's not this. Last part of the last section. Oh, I don't know. Yeah, so we need to talk the last section, not last section, the last no star section of martingales. Okay, so I just talk. So if you ask questions, you want me to clarify, I will stop and using iPad. So otherwise, I will just talk to the board, right? talk to the computer. So this is called optional stopping theories. We already have several, right? So basically, right, this tells us, right? So some inequality or equality, right? With martingale, usually we have equality of some expectation of the random variables or random stochastic process, but usually we want to use the stopping time, because given stopping time, we can say something interesting, right? So this is actually very, very important techniques, right? So we're introducing stopping time, we can say something more about martingales or stochastic process. So this is just one example. Okay, so I will just start, right? So this actually theory is a theory in section 4.4, maybe 4.4. So when we're talking about the LP or Dubs inequality or something. So for instance, if we have xn, right? If we have xn is a martingale, xn is a martingale, and we have two stopping times, right? So previously, m and n. So previously we can show, so if both m and n, right? If n is bounded, uniformly, let's say n is like this with this condition, right? Is less than some integer k, almost surely. So we call m and n like bounded stopping time. So then we can show the expectation of xm is also controlled by expectation of xn. Yeah, give me like 2 seconds. Sorry. Okay. So this is very easy to show, right? Because we already have the boundedness of the stopping time. Okay. So this is also right. If we change xn to martingale, so here the inequality becomes equality, right? So this becomes equals, right? So if you change this to martingale, so all the discussion below, right, also holds, right? Also holds for not all, right? You need to change the setting a little bit, but if you change the setting a little bit, so you can write a similar theory for martingale or super martingale. So in particular, right? So we change this to martingale, xn to be a martingale, and also we have two stopping times which are bounded. So then we have this conclusion, but change this to be equality. Right? So this is problem 2 in midterm. You can find proof below, and we just follow the proof in section 4.4. Okay, so but now sometimes, right? But sometimes even in very easier setting, even in some very easier setting, we need to treat only the stopping time, right? So yeah, so those stopping time might be finite almost surely, but it might grow to infinite, right? For instance, right, if you there's when we consider stopping time, like the exit time, right? When we consider like symmetric random walk on 1D. So yeah, you will see this example later when we consider the stopping time like exit A and B, right? Sometimes if we send B to infinite, right, this N actually goes to infinite. So yeah, so for many cases, right? So I mean, so this stopping time might be unbounded, right? So we need to be able to say something like this for unbounded stopping time. So all the theory called optional stopping theory. Yeah, why it's called optional stopping? So maybe it's related to optional. Maybe come from I don't know really for sure. So it comes from the stock market terminology. But yeah, okay. So let's see the first theory. Let's see the first theory. It's called. So the first theory, right? Say if we have a uniformly integrable submartingale, yeah, so then, so for given any stopping time n, so xn, if we define a new stochastic process, a new martingale, so this is uniformly integrable. Okay, so this, right, so we know, so maybe I just tells you the idea of the proof first, then I can show you the details. So yeah, so if we have a stopping time n, right? So this is a submartingale, and this is also a submartingale, right? It's a basic property. It's the basic property of martingales. So how to prove this, right? How to prove this? So here is not a very hard proof. So so I can tell you, right? Basically, if we have, so let's say, so we have, so this is a stochastic. This is a submartingale, right? So let's say if this submartingale converges to something, let's call this xn. So and then goes to infinity, right? So if, so this stopping time equals to infinite, right? So then this is just x infinite. So this x infinite is just the Euler limit of this uniformly integrable submartingale. Okay, yeah. So previously, right? Previously we already know, right? So let's just consider this xn, right? So this xn, so we can use in the martingale convergence theory, right? So as long as we have the positive part of this submartingale is positive, not positive, is uniformly bounded. So actually we can have the almost surely convergence of xn, right? We can have almost surely convergence of xn. So then, so by trick, we can show this also works for, so this new submartingale. So for xn, so they have almost surely limit x infinite. So this also have some almost surely limit. And also it gives the limit is bounded in L1. So this actually can tells you the new submartingale is integrable. But this is a very vague explanation. So if you have questions, I can answer now. But otherwise, I will explain in details. Okay. Okay. So maybe let me write a little bit. It's better to write somehow. It's better to write. Okay. Okay. So all those can be saved. I will we send you later. So basically, you don't need to take notes. I mean, it's also very weird to take notes, right? So let me show you how to prove, right? So what we have here, right, is first we have xn, we have x. So this is a uniformly integrable submartingale. So uniform integrable actually, right? So we can use the martingale convergence theory. So for martingale convergence, convergence, so we only need the positive part is uniformly integrable. So, but now it's all finite, right? So actually this implies xn converge to x infinite almost surely, right? So now we can get the convergence almost surely, right? So there exists this. There exists this. So, and also in L1. So why in L1, right? In L1. So this part actually is from this. It's from the uniform integrability. So this is from like the L1 convergence part. Okay, so this is just for xn, right? For xn. And also we can do this for we can do the same thing for this. Yeah, so we can do the same thing for do the same thing. We can do the same thing. Okay, but if we want to show, right, we want to show this also converge, right? Is this also converge to xn almost surely? So as n goes to infinity, so we need some bound, right? We need some bound. We need some bound. So so how to estimate, how to have this bound, right? So this actually is very easy, right? We just use the previous one. So how to get this? How to get this? So we write xn plus, so which is the positive part of xn, and this is a submartingale. So this is submartingale. Okay, so use the previous, so we can using the previous inequality, right? I just show you, so we can get this, right? So this is a submartingale, right? So this is a stopping time, and stopping time is bounded. So we have this control, right? We have this control. And we can put the supreme there, right? So we can put supreme there. We can put supreme there. And this is finite, right? By uniform integrability. By uniform integrability, okay? So now we can use, so now we can use martingale convergence theory again, right? We can use martingale convergence theory. Again, but for this submartingale, right? This is a submartingale, and we apply the martingale convergence for this. So we have the convergence. So we have convergence xn, right? So almost surely. Almost surely. So this is and so if n goes, if n spring time is the infinite, right? Spring time is infinite. So then, so it's just xn goes to x infinity, right? So, and also we have this, and also we know the limit is in L1. So this is all the martingale convergence theory. So this is finite. Okay, so this is what we get, right? This is what we get. So basically from this condition, we can show, so we can conclude, so this is uniformly integrable. So why, right? So why this is uniformly integrable? So this not only from this condition and also so xn is uniformly integrable, right? So you can check this, right? So you can check this by so I just do the checking. Just to do the checking, maybe I use this. I can just do the checking. So to show this sequence, is, so to show this sequence is uniformly integrable, right? We need to show, so this is small, this small, when k is big. Okay, so how to show this, right? So here actually, so we just using we just do the decomposition. So either, right, so there are two cases, right? There are two cases. Either the stopping time is bigger than n or less than n. So we have two parts. So xn bigger than k, n less than n. Okay. So if the stopping time n is less than n, so now this become this, right? So yeah, that's it. And the second part, so xn, which is bigger than k, so if the stopping time is bigger than n. Okay, so for this part, so I just do a little bit quick. So for this part, so it's okay. So why, right? Because this part is less than e xn bigger than k, right? And so xn is uniformly integrable. So this part is small. Actually small. This part small, right? Since xn is integrable, uniformly integrable. How about this part? So this part actually, so equal, maybe less than equal to xn, right? Since xnk, right? So xn is L1. So it's small. This is small as well. Okay. So this is like detailed proof. This is the detailed proof. I will go back to, if you have questions, you can ask. So before I go to the, yeah, I will share the notes to you, but you don't need to take notes. Okay, so go into sharing. Okay, so can you still hear me, because it says the connection is unstable?
Yep, I can hear you.
Okay, okay, you can hear me, right?
Yes.
Okay,
Yeah.
good. Okay, okay, good. So I just go back to the theory. So this is the theory I just showed you. So if x originally is uniformly integrable, so then given any stopping time, so this stopping time can be unbounded or anything, right? So if we do the composition of stopping time, we form a new uniformly integrable submartingale. So this is uniformly integrable. And so what we can say, right? So we can say this has a almost surely limit and also have a L1 limit, right? So that's very good. So basically, right, the original property for this stopping state process. Um, so and if you compose with any stopping time, so we still have the same thing, right? Stopping time doesn't change change a lot. So this is the interpretation. So you can see the proof there. Okay. So from the proof, right? From the proof star, let's say see the star, right? It's a proof star. So you can see what we really use, right? Is this part is small, and this part is also small. So basically, right? If you already know, right? Uh, this is L1, right? The X capital N is L1, and also we know this Xn this part, right, is uniformly integrable. So we can directly get this is uniformly integrable, and we can use the previous theory and get Exn Ex0 is less than Exn. So this is just direct checking within the martingale property. If everything is changed to martingale, right, this is equality, right? Not inequality, it's equality. Okay. So okay, so this theory, right, is, so it's also a direct application of what we showed before, right? So you need to know, right? You don't. So sometimes it's more important to know how to use this, right? So then know the proof, but when you learn this, it's better to know everything. Okay, so this theory says, right, so if Xn, right, is a uniformly integrable submartingale, like the setting we used in the theory we just showed, so we know this is a uniformly integrable submartingale, and we have stopping time n. This stopping time can be finite or infinite, right? So it's any stopping time. So then we have this inequality, right? The initial expectation is less than the expectation of X capital N and less than the limit. So as I said, right, so the Xn is uniformly integrable, right? So this is definitely has almost surely limit and has L1 limit as well. So this is the almost surely limit, X infinity is the almost surely limit, and also the L1 limit. So we can have this, right, again, right? So if this Xn is a martingale, right, not just a submartingale, so then here the inequality becomes equality, and this becomes equality. Okay. Yeah, maybe I'm too fast. Okay, the proof, as long as we prove the previous theory, so this is very easy, right? So we since Xn is a submartingale, right? So this is the theory we proved, right, in the very beginning or in section 4. So initial This is a stopping time. So this is a stopping time. So this is also a stopping time. Right? So n, right, take the minima because between the capital N and the n, right, is definitely less than n, right? So we have true, we have the inequality. As before, right? As before we showed, right? So we know xn is uniformly integrable, right? We have the almost surely and also L1 limit. Again, right? We already show, right? This is also uniformly integrable, right? So we have almost surely and one limit, right? So that's why we get xn, right? And right, since this is L1 limit, right? The inequality is preserved, right? We just send n goes to infinity, and this is what we get. Okay, so again, so for some cases, right, we want this equality, right? So that's a very important tool to getting some quantity, right? You want to say something about exn, right? About xn, right? So like the exit time, right? Something. So this is basically two. Basically two. Okay. Okay. So this is again, right? The same thing. Same thing. But instead of consider, so I just go fast. Then I will show you maybe two examples. So
Sorry, can I
I
ask a
suggest go
question?
through. Oh yeah, sure, go ahead.
Can you scroll up to the top?
This one.
No, the proof of theorem 4.8.1.
Okay.
Yeah, here. Yes, here. Where did in this bunch of equations, where did you use x n maximum of minimum of n goes to x big N almost surely?
Here I use nothing. You mean this part, right?
Yeah, in this part you didn't use x.
Yeah. So this part I only use two. So first, this is small. So why this is small when k is large, right? It's because xn is L1, right?
Yeah.
It's integral. So, and also we use the uniform integrability of the sequence xn, right?
Yes. So you don't need x big N
Yeah,
minimum N goes to xn.
Okay, so
Yes,
we
here.
don't need, right? So this is what we need uniform, we need this, right?
Yeah, to get
We need the positive part is uniformly bounded, uniformly integrable, right? To get the almost surely convergence.
Why do we need the almost surely convergence?
The
next page didn't use the almost surely convergence.
Yeah, but so okay. So first we need the almost surely convergence, and this is integrable to get this.
Oh, okay. We only need the x big N is integrable, right? We don't need almost surely convergence.
Yeah, we don't need the almost
okay.
surely. Yeah.
Okay.
Yeah, but since this setting is stronger, we actually have almost surely convergence, right?
Yes.
So yeah, you're right. So like in this setting, we also have very strong conditions, right? So that's why we also have almost surely, right?
Yes.
Of course, you are right, right? So we don't need almost surely, right, to have this, right, to have this result, right?
Yeah.
Yeah, to have this result, we don't need almost surely. But since this condition is so strong, we also have almost surely convergence. Yeah.
Yes.
Okay.
Okay. Yeah.
Yeah. So yeah, keep asking questions. Otherwise, I'm too fast. I because I cannot see you. So I cannot see students. Okay. Okay. So this is a theory, right? On the super martingale, right? So we have a non-negative super martingale. So basically, we already have convergence, right? So because we don't need to control negative part, right? So for super martingale, we need to control like some negative part, but now we already know it's non-negative, right? So basically, we have the convergence surely and in L1, and we have the same result as before, right? So but with the reverse direction inequality, right? So this is what we have. So basically, we just do so. This argument, right, is very easy, but very standard argument. So right, so it's just the previous, the first theory I showed you, right? So you have two stopping time, right? So this is stopping time, this is a stopping time, you have the inequality, right? So because this stopping time is smaller than n, right? So we have the inequality, right? So here is the super martingale. So the direction of the inequality is reversed. Okay, so by this, right? So this is kind of we do the truncation, right? And time n. So then we send n goes to infinity, and using Fatou lemma, right? So this part using Fatou lemma, we could recover EX. So this part we apply Fatou lemma, we recover the almost Shuli limit or L1 and also L1 limit of x infinity. So this is a statement on super martingale, right? Of course, right? So this is if this is martingale, non-negative martingale, right? So here is equality. Here is equality. Here is equality. Here is equality. Yeah. Yeah, it's right? Because it's all equality. It's all equality. Yeah. Okay. So the following is a bit too fast, but you can. So if you have a textbook, yeah, post, but maybe I don't. So this I basically just copied the theory from textbook, right? So you have textbook there, you can have a look at that. So Xn is some martingale, right? If the increment part conditional the project to Fn is bounded almost surely, so then everything. So I won't say anything about the proof is a very straightforward checking using the following inequality. But I will show you several applications now. So to show, right, the stopping optional stopping theory, right, is useful, right? In some cases, it's very useful. So I just skip this, right? When we need this, I will go back to let you see, right, this theory.
Hi, I have a question.
Yeah, go ahead.
Yeah, so the last theorem that you showed, I mean, in the one before it, you didn't assume the uniform integrability of xn, right?
We don't need that.
But then how do you get that expectation? Oh, okay, okay. Thank
So
you.
here,
Yeah.
right, because this is a supermarket, right? To have the converging theory, we only need to control the negative part, but here is already non-negative. So basically, we already have, for this part, we already know, right, everything, right? So then we just use Fatou. So to using Fatou lemma, right? So we only need some non-negative property. So
Yeah. Okay.
yeah.
Can you explain Fatou's lemmas here again? The two inequalities that you used. The first one is directly for super martingales. Why did you use
let me write a bit, right? Let me use the iPad again. Okay. So how to use the Fatou, right? How to use the Fatou? So I always, so for Fatou lemma, right? So what is Fatou lemma? So, just a Fatou lemma. So for instance, if we have a sequence of functions or variables, right? If it's non-negative or control from below, so then Fatou lemma says the following. So d mu, right? Mu is just a mirror, right? Just a mirror. Let's integrate on x. So if we take the integral first, then take the mean. So actually, this is bigger than we take the mean first, then take integral, right? So here, right? So here, So here exn, right, with an n goes to infinity, right? So n goes to infinity. So this should be bigger than lim n goes to infinity. Exn, yeah, maybe I should be more careful. So this is
I think
exn.
why? I think the direction of the inequality is
So
flip.
this is like that, right?
Oh, yes.
Xn. And so this definitely is right because we have almost surely convergence. So this is exn. And so why?
Is this because of the L1 convergence for the last equality?
So you mean this one bigger than this? So how to get this, right?
No, the equality. Why is the expectation of the lim inf x n minimum n equal
You mean
to
here?
Yeah, this is L1 convergence.
So this, okay. So we have the almost surely convergence, right? This is just xn. So this actually equal, right? So why this is true? Because this part actually is not just a lim inf. So this part actually is because this is
Limit.
yeah. Yeah, it's not just lim inf.
But
This is just xn.
But xn goes to x doesn't mean almost surely it doesn't mean expectation of xn goes to the expectation of x.
I don't. So can you repeat?
Convergence almost surely doesn't mean the expectation converges.
Yeah, you're right, right? So that's why we use Fatu, right? So we do this first, then we take expectation, right?
Oh, right. Okay.
Yeah. So this is first. So that's why we already changed the limit inside, right? So
okay.
Yeah. So this is true.
And what does the first inequality come from?
First, this one.
Yeah.
This is just from the. So originally we have right. We do the truncation, right? So we this.
Oh yes, and then take the limit. Okay.
Yeah, we have this. So but the problem is why this is true. Okay, so why this is true? So first exn actually converge to so let me double check this. So this cutting L1 or so yeah. So let's so the first half is not is the problem. The problem is this part, right? So the problem is why exn is bigger than x infinity. Problem is this. So let me see. we
But the
have
state,
the,
but the
yeah, go ahead.
but the statement of the theorem
We have
only,
this, right?
but the statement of the theorem is only expectation of x0 larger than expectation of x big N. Why do you need the last inequality? The theorems, the
Yeah.
theorem 4.8.4, the conclusion is expectation of x0 larger than expectation of x big N.
Okay, let me go back to that. Theory 4.82, you say
4.8.4. Okay.
here. Yeah. So what's your question?
But on the book, this theorem 4.8.4 is just the first inequality. There is no second inequality.
Okay.
I think the last inequality is not true.
Yeah, maybe it's not true. Okay, let me
But
just write.
But the book is very strange. It says the first inequality, but then it mentions x in infinity. I don't know why it mentions x in infinity.
Ah. Okay, you are okay. Oh, I think that's just I just yeah. So in the textbook, they didn't say anything about the last inequality. They didn't say this part, right?
Yes, but the textbook also mentioned x in infinity, which I don't know why. It says where x infinity equals to limit x, and which exists.
So
right? So that's why I write x infinity there.
So actually, the book tries to mean that if your n is actually infinity, then the right hand side of the inequality will be like expectation of x0 is bigger than equals to expectation.
Yeah,
Okay.
definitely right.
But if n is not in infinity, then it's not necessarily larger than x in infinity.
So can you like find an example? Yeah. So when let's say n, the capital N, the stopping time is infinite. So this equals, right? Let's say when n equals to infinity, right? This equals. But okay, no lasting quality. So that makes sense, right? Because so let me go back to here. Not really. Okay, let's go back to here, right? So that's why when you ask a question, I feel right. This is the problem, right? This might be wrong. This might be wrong because right. So when you take when you're using file 2, right? So this for this part you can really using lim, but now you cannot, right? So because here there's already inequality here, right? So we what we can say, right, is lim this is bigger than lim exn, exn. So yeah, so here this is bigger than exn, right? And definitely this is bigger than ex infinity, right? But we cannot say these two, the relation between these two, right? Okay, bless you. Right. So you have some idea on? Right. So we don't have a relation between these two, right? Because these are both. The only way to make this true, right? This should be something like that, right? These are all in, right? Not lim in, right? And this we can say, right? Otherwise, we cannot say anything. Yeah. Okay. Yeah. Let's go on. Let's go on. Okay. let's go on. Okay, so this theory basically you have a submartingale and you have the boundedness. So between the increment, right? The conditional expectation of the increment is bounded. Then we have and also given one right, integrable stopping time. So then we have everything, right? Then we have this is uniformly integrable, and also we have this inequality. This inequality. Okay. Okay. Yeah. So here, if we change some martingale to martingale, right, so it become equal. Here become equal. Okay. So we will use this. So let's see a very easy application. We talked we mentioned this actually already twice before. So last semester one time, and so when we're talking about random walk, we also prove Walls equation. Okay, so let's consider like random walks, right? So cos1, cos2, right? This sequence is IID, and Sn is the sum of first n terms, right? So S0 is a constant, right? So Sn is a random walk. So we write we write the filtration Fn generating by first n terms. First n term. So if we write xn, right, we normalize, right, we normalize the random walk by minus their expectations, right, their mean values, right. So xn is we can very easily check xn is a martingale. Xn is a martingale with respect to the filtration Fn here. Okay, so in previous previous theory here, in this theory is element, so have the uniform integrability. We have the uniform integrability and this, right, and this. Okay. So we can use that. We can use that. Okay. So how to use that, right? So we just check the condition. So xn, so this is the increment. So xn is the random walk, right? Normalized random walk, right? So n minus 1 minus xn actually just cos I, right? Cos I minus mu, right? These are independent. The increment actually is independent of the past history Fn. So this is just the expectation, right? Of course, the expectation is bounded. So this is less than 2 mu, 2 mu is finite. So if we have stopping time, which is L1, right? So we can use the previous three, right? But now it's for martingale, right? Not some martingale. So we have the equality. So Exn equals to Ex0, right? Ex0, right? Is if you take n 0 here, so this is just 0. So Exn, right, equals to 0, which gives us the Walls equation. So Walls equation, right, is the expectation of Sn equals to mu times En, right? So mu actually is E cos I, right? E cos I. So this is a generalization of the linear property of Sn. So if here capital N is a small n, right? So it's very easy to check, right? So this is just n, right? And this is just the expectation as well, right? So it's Walls equation. So we proved earlier, and here if you use the this theory, right? This theory, but for martingale, very easy to show. It's very easy to show. So I go fast because this we already show. We have proved this before, right? And you can see right now the proof is easier, right? Because yeah, go ahead.
Is this conditional expectation just expectation?
Yeah, it's just the expectation. You mean here, right?
Because everything is yeah, here.
Here.
Yeah, because everything is IID.
Yeah, everything is IID. So if so here is just actually cos n minus mu, right?
Yes.
So cos n minus mu, not cos n. So cos n plus 1. Yeah, plus 1 minus mu. So then this is just usual expectation, right? So it's a number, right? It's a number. So this conditional expectation actually is constant, right? It's a constant, it's a number, so which is finite almost everywhere, right? So it's, of course, it's finite almost surely. Yeah.
So where do we use this?
We use here is we use the condition, right? But not for, but here we change a little bit, right? So this is for sub-martingale, right? But the xn we define is martingale, right? So this is equality.
Can you go back to Walt's theorem?
Okay.
I still don't understand how we got the equality.
Okay, you mean you still don't understand why this become equality, right?
Yeah.
So this is because this is a place where we use the equality.
How do we get this?
How to get this, right? So it come from here, right? So that's why I said in the very beginning. So
it
this
comes
theory,
from here. Okay.
yeah, from here, yeah, from here. So we need a theory, right, instead of martingale, right? Instead of sub-martingale, we need a theory for martingale.
Okay.
And then we need to kind of go through. Yeah, maybe I should put this as an exercise, right? A homework problem. So you can go through this. You can go through this. And go through the theory, and just write a new theory for this. Yeah. So you change x into martingale, right? Basically, the only thing changed is just here. Yeah. So the idea is the same, right? So here you take some, this is n, right? You take some, you take truncation, n and small n, right? So for martingale, right, this is always equality. So that's why in the end is already get equality, right? Because L1 convergence, right? L1 convergence. Since this is uniform convergence, uniform equal, right? So these are equal, right? So that's why in the end, right, for martingale, you can get equality instead of inequality. Right? Okay, this is one like a very small application. So I just move to, so since we don't have a lot of time, we only have 7 minutes. So I won't talk about symmetric random walk because we already know this, right? Symmetric simple random walk. So I talked about this earlier, and you can check this very easily, right? So if you have a symmetric random walk, we have symmetric random walk. Yeah, so if you don't talk, you can mute that, so it will be more. Okay, symmetric simple random walk, right? So this part we already know, right? For instance, if we define a stopping time n, and the first time the particle exit A and B, right? So it's starting from, there's a random walk, right? The guy starting from X, right? Then doing random walk, symmetric random walk. So the stopping time is the first time he exits A, B, right? A, B. So here A, X, B are all integers. So they must visit all integers, right? So, like consecutively. So then this is what we already know. So the probability, right, starting from X, exit and point A, right, is this. So is this length over the whole length, and the probability exit from B, right, point B, right, is this length, right, over the whole length, right, whole length. So this we already know. But there's another thing we don't know, right, but we are clear now is the following. Is asymmetric, it's not symmetric, simple random walk. So let's just mention this. We don't have time. So So we have a symmetric simple random walk, simple random walk. Okay, instead of the symmetric one, so probability CASA I equals 1 is P, probability CASA I equals -1 is Q, right? Q is 1 minus P. So P is not equals to Q. Okay. So in this case, right, so we can do the similar thing, right? Similar thing. But now, right, so we consider a new quantity, right? So previously there's no this quantity because this is always 1, right? So then this is just always constant 1. It's not very useful. But for asymmetric simple random walk, right? So it's we define this quantity like Q over P to Y, right? Y is integer. And if we consider this, the phi Sn, so this actually Sn is the sum or the random walk, right? The sum of first n terms. So then we can do the same thing. We can do the same thing. So Tz is the first time Sn, the random walk visit the point Z, right? So if we're starting from A, right, and we want to compute exit time at A and B, right, the probability, so then we can do the same thing. So this is the probability from X, but exit from A, right, so this is the probability, right, instead of original B minus X over B minus A, now we consider function phi B minus phi X over this, right. The idea is exactly the same, So first to show this this function phi Sn is in the martingale, we can use the Walls equation. We can use the Walls equation. Okay, so we choose n as minimum one of the 2 stopping time, right? So this is again stopping time. So S so this S definitely is not a martingale. So if you normalize it, it's a martingale. Sorry, let me see. What is S? Sn is just the first n terms. It's just the first n terms. So this is so originally, right? We in the first step we show Sn is a stopping is a martingale, right? So we do the composition with the stopping time. It's also a martingale, and phi actually is always bounded by 1. Is that true? So according to the definition, not necessarily true. So Y is always bounded, right? So because already taking stopping time, right? This is the definition of phi, right? Since Y is bounded, right? Since Y is bounded, right? If we impose the stopping time, so actually Sn is restricted from A to B. So this is definitely bounded quantity, right? So it's integrable. So all the integrability are satisfied. So we can use the previous theory, right? So since this is bounded, so we can use all the previous discussion, right? So bounded means like uniform integrability, right? It's stronger than L1 actually. So we can do the equation, right? So this is the initial state. This is expectation of S, right? So we just expand everything. We can compute the probability. Okay. Yeah, we have no time, so let me see. You can check the small exercise here. So for instance, right, if a gambler is playing a roulette and betting $1 each time, right, this probability of winning is like 18 over 38. Right, the probability of losing is $1 is 20 over 30, right? So you are doing some gambling, right? So definitely on average it's not a fair game, right? Otherwise the casino won't make money, right? So if you have like $20, right? If you have $20, so you're starting from $20, right? You say if you win $40 and you leave, right? So you can compute the probability she reached $30 before losing her money. So this is the computation. We're just using the previous formula, right? So we choose P equals to this, and this is 1 minus. So actually, right, so the probability you win $40 before you lose all your money, right, is almost 10%, right? So So even this probability looks very, I mean, even it looks like a fair game, right? The probability right go is like reach $40, double your bet, right? Before you leave, so the percentage is really low, right? So if you keep playing games, actually the casino will win a lot, right? So because they have larger number, right? So I mean, yeah. Okay. I think I will basically stop here. But before I really stop here, let me just say something. Just say something. Okay. So first I make some announcement in Canvas. So you can, so if you are not available, so actually today there are like 25 or 24 students here. So that's actually a lot because most of the students are here. Maybe even, I mean, so, but so not available, we will have videos recording, but this is usually it takes like 5 days to get that. But I will show you some materials which will be useful. Okay, so so there are two courses from MIT. So those two actually are very famous professors, right? So the first one is by Scott Sheffield. So he's very famous, and he kind of had a chance to get Fields Medal, but in the end he didn't. But this course is very, so I might use his slides from next lecture. You can see there are no videos, but they have slides, right? I will maybe starting from here first. I will maybe use some of his slides because his slides is very good. And sometimes it looks better than Durant's textbook. You can go there to see. I mean, first read the textbook because it's very comprehensive. You want to know everything, right? That's the best reference. Otherwise, if you want to know in some context, you can read other textbook. Okay, so there's another one. Sorry, I don't know. There's another one I mentioned to you last semester. So this is called discrete stochastic process. The order of this course is quite different to ours, but I think it's very clear, and the instructor is very famous. I think he is very famous. You can definitely find, he has Wikipedia. And you can see, right, the Markov process and random works. The order is quite different, but it's more for engineering, electric engineering students. But you can, yes, for instance, there are not many discussion on martingales, right? So not I mean, in deep side, it's not comparable to our textbook, but you can still read that. I will post several homeworks today, a little bit later today, and from next class, I will maybe use some slides from Sheffield, and also let me know, right? So how, your feedback about today's online meeting. I cannot see anything, but maybe because I just talking, right? I don't see the feedback. If I have the video, it might be better understanding of this. Okay, anyway, so I will, so if you have questions, I can answer, but if you have other things, you can leave now. So if students have questions, I can keep answer, but otherwise, have no questions, I will end the meeting soon. Yeah, if you, so you can unmute, right? So. Okay. Okay. No questions? There's one student. Okay. Okay.
I have a question regarding to the start of the class, the finite theorem, the application of the finite theorem.
Oh, okay.
I didn't understand that binary example, theorem 4.7.10.
Okay, so let me go back. This one, which one? This theory?
Yes. Why is this an application previous? What is a big F theta corresponding to?
What is big F theta? You mean previously, right? I don't know. So the previous theory, so basically it's like abstract theory, right? Doesn't construct this F. So the previous theory says, right? So if you condition on that, right? So so this is the previous theory.
Yeah.
It's more general and abstract.
If some random variables are exchangeable, then it means that they are identically distributed, right?
Yeah, but conditional on this.
Then they become
this like magical.
No, if we don't conditional on this, then they are still identical but not independent, right?
Yeah. So
Okay.
they're not independent. Actually, their cases they are really correlated, right? They're really correlated. Yeah.
Yes.
So the information of the specific definite theory, right? 0, 1, the not 0, 1. This very specific. This is actually the first version of definite theory. For this theory, right, the very magical information of the E of the exchangeable sigma field is just here, right? It's just encoded in F. Yeah. Yeah.
So the thing under the integral theta to the power of k1 minus theta to the power of n minus k. What is this? Is this like some?
Oh, what does this mean, right? So theta actually the probability, let's say heads up, right?
Yeah, binary.
Yeah, binary. It's binary, right? So here you see, right? So that k terms up, and n minus k terms down. So if we already know, right? If we already know the information, if the let's say the coin is a fair coin, right? So when we compute the probability of this, right, it's just a 1/2. I mean, it's equal, right? It's 1/2 to k.
But the constant term is ignored, right? Put into the F term.
What? Yeah. So
there should be some constant like from n choose k.
And
oh no, no.
This is fixed.
Oh yeah.
Fixed
sorry.
order,
Yes,
right? This is fixed order.
Okay.
Yeah. I will anyway. So I will post the short paper on. You can read that. I will. So I found this short paper. I mean, it's really not that important paper, but it's a very interesting paper. So you can see the proof of this, like in several pages. Yeah.
Okay. Thank you.
Okay. Yeah. Okay. There are 4 participants now. So if you have, you can ask. Otherwise, you can leave. Okay. One question. Hi, Zhenfu, can you hear me? Yeah, I can hear you. Yeah, you can ask. You can ask. So there are 3 people: Cai Chengshu and Zhang Jiayao here. Yeah, you can ask. Yeah, you can just say it. Okay. So maybe I just end the meeting. If you want to talk, we can talk like separately, privately. I will end the meeting. Yeah.